from the Friedrich-Alexander-University of Erlangen. He's a postdoc researcher there. He got a fellowship by the Bavarian Research Institute. He won the Best Paper Award in 2022 at the ACM on nanoscale computing. And he's mainly working on modeling systems for molecular communication, running Testbed, and do a lot of research there. Participated a lot of summer schools and tutorials already. So, and hopefully this enables him to explain now very well to all participants what is molecular communication and what is a topic you are working on. And on this nice project you're working on, I already saw that picture there. Okay, the next stage is yours.
Yeah, thank you, Christian. It sounds a bit like that I'm only traveling to conferences, but yeah. Okay. I will explain you a little bit about one of our ongoing research projects at FAU, where I'm mainly working on. And I came from theory and went to praxis now. And hopefully later you will understand why chickens can fight cancer. And before we start, as Christian mentioned, he said some of you or many of you don't have an idea about molecular communications, right? So maybe just raise your hand if you don't know what molecular communications is. Okay, so just a few. However, I prepared a short introduction for you just to motivate that, because the topic I'm actually working on is maybe at the other end of the relation to conventional communications. So for that, I think you all know the top picture, like a conventional communication system with a transmit antenna and a receiver antenna. And in between, we conventionally use electromagnetic waves to transmit zeros and ones. So this type of communications is mostly based on waves, electromagnetic or acoustic or whatever. And the main problem with these type of communications is that they are not suitable for communication in liquids because you have very high damping. Also on the nano and on the micro scale, such communication systems are not super suitable because you need very small antennas or you need very high energy to transmit anything. And also the communication with biological systems is very complicated because how should a cell know what an electromagnetic wave means? So that is one side of the coin. And the other side is now we have a lot of natural communication systems, which are very often based on molecules. On the right-hand side, you can see an example which we all might know. These are bacteria. And what they do when you got infected, bacteria constantly exchange molecules with each other. And they exchange them not only to communicate, but also to coordinate. So for example, if we get infected, these bacteria start to communicate with the command to grow and reproduce, as long as they are enough that they can attack. So here we have systems which can communicate by the means of molecules. And this type of communication is suitable for communication in liquids on the macro, micro, or nanoscale, and also within biological systems. So there are even more examples. So for example, quorum sensing, this is the picture on the right-hand side, but also synaptic communication or hormone distribution. So for example, when you fell in love, you can feel this everywhere in your body, and it's nothing else than broadcasting this information into your body. But also insects and plants are communicating by the means of molecules. And all this has spawned the idea of synthetic molecular communication some years ago. So the first papers were around 2004, and then the field is growing and growing over the years. Especially in Germany, we have now a lot of research projects going on in different directions. So now what is the idea of synthetic molecular communication? So here on the top, we can see again the conventional system, and here we can see a molecular communication system where a transmitter, let's call it nano device, this can be a cell or something synthetic, is releasing molecules in a biological environment, and we have a nanoscale receiver which is able to detect this information. And compared to the conventional system, the information here is encoded in the properties of molecules. So for example, in their concentration, in their type, in the time of their release or something. And by this synthetic molecular communication, we want to enable this communication or information exchange between nanodevices or with biological systems. And the expected benefits are, there are several ones. So it's applicable where conventional communication cannot be applied. It's, in most cases, inherently biocompatible. It's energy efficient. And as we are inspired by natural systems had billions of years to develop to be very efficient. And exactly with this knowledge, we can also build very complex systems with complex processing operations. And all this has spawned this innovative and interdisciplinary research field with a lot of groundbreaking envisioned applications. So maybe to summarize a few of the applications, and this is just a selection of them. So we have a lot of different medical applications where we can apply molecular communication. So for example, we can think about that we have smart implants, which maybe are able to detect plaque, which is also an ongoing research field. So Alex and Pitt are working on these things. And then this smart implant is connected to the outside by an antenna, for example. Or drug delivery. So drug delivery is a very prominent field in pharmacy, for example, and the main idea is that we want to deliver drugs to the place where they are needed. So when you have cancer, instead of getting chemotherapy in your arm and the drug is spreading your whole body, you have small nanodevices which are loaded with drug molecules. However I do that, I guide them to the tumor and release my information, which is the drug in this case, next to the tumor so that I can increase the efficiency of the treatment while I can reduce side effects. And this is one of the applications where molecular communication can play a role. The same is the other way, like health monitoring, but we also have a lot of other applications. So for example, pest control for smart agriculture applications, or maybe monitoring the health status of plants in greenhouses, because also plants release different types of molecules when they are stressed, when they are out of water, when the ground is too salty. This all leads to different types of molecules which are released. And however, all these applications, they spawned now a lot of research, and there are a lot of ongoing challenges which need to be addressed. And I always tend to stop this introduction now with the challenges, because this is basically where the field is working on currently most of the time. One thing is hardware design. So we know a lot about antennas, but as I said, antennas cannot communicate with cells, and also an antenna can only hardly receive molecules. So we need suitable hardware, like nanoparticles or modified bacteria or something else, which are suitable to be used as transmitters and receivers for these molecular communication systems. And alongside with hardware, we also need suitable signal processing methods, because this hardware we are designing, we want them to do something like detection or processing or filtering or whatever. So we need to find a way how to chemically implement suitable signal processing methods. And for example, later, Alex will talk a little bit about how we can do this, for example, by chemical reaction networks. And then this is maybe more related to here, we need also suitable communication concepts, because let's say our body is communicating constantly, but maybe these communication processes are not the most efficient ones in the Shannon sense, but they are working, so they are efficient. So especially here, the concepts from identification or goal-oriented communication are way more suitable ways to go. And this is also something where the field is working on. And then maybe here we also need modeling and simulation techniques, and this also makes a huge basis of the literature. So we have to understand these biological and chemical systems and try to find suitable channel models for the propagation, suitable models for detection and modulation and all these things. And the last thing is experimental testbed development. And that is where, let's say, I started here, tackled all the others, and ended now up with my main work in experimental research. That is at the moment what I'm focusing on, and that is also what the rest of the talk is about. But before we start with the testbed I want to show you, I motivated a little bit more because I want to go one step further in these medical applications. And now also I maybe lie the basis for Stefan's talk tomorrow, because I think he will talk a bit more about the Internet of Bio-Nano-Things. But I need this idea a little bit to motivate the medical applications. So let's shortly talk about the Internet of Bio-Nanothings and what this means. It's basically the plethora of all these medical applications in Molcom has spawned the idea of this Internet of Bio-Nanothings. And it's, in a rough picture, very easy. So we have here maybe our well-known Internet of Things, where we have multiple IoT devices which are connected via the internet, so then they can do processing and sensing tasks. And now the idea is that we extend this to inside the human body. So we have now in-body networks which are connected to each other by molecular communication channels. So for example, we have an in-body network of nano devices here and nano devices here. And also these nano devices have sensing, processing, detection, and transmission capabilities. So what could be a use case here? So if I have an anomaly here, for example, so this is the red blob. I don't know why the mouse has gone now again. And an anomaly like a tumor has the property that it changes its environment. And then maybe one of these networks consists of sensors which can detect this change in the environment. So they can detect the existence of this tumor. And then the network takes this information and forwards it to a suitable interface. And then we further transmit this information through classical communication methods to a healthcare provider where a decision is made. And then I transmit a decision back to the in-body network and maybe can directly start or initiate the treatment of this disease I've detected there. So this is all rather, let's say, in the future, but on these concepts are people who are working on medical applications of molecular communications. And maybe you can place all of these things we are doing somehow in this overarching framework here. The two main challenges are then, just to summarize this again, maybe again, one is sensing, what we are mainly working on. So this means sensor nanomachines maybe propagate in the vascular system to detect the disease, and then they report this detection by the release of suitable molecules. And we have targeted treatment. So we also have in these network actuator nanomachines, which receive information either from the outside or from another nanomachine, and then they start the treatment of the disease. And maybe again, and this is a little bit of a repetition, we have now all these challenges towards the realization of this Internet of Bio-Nanothings. And I said this already, we have this hardware design, signal processing, communication concepts, experimental test beds, and modeling and simulation. And maybe one point I want to make here that we started all to work interdisciplinary, because these challenges, they cannot be addressed by a single research discipline. So because for example, I'm from signal processing or from engineering, so how should I know what type of chemical or biological hardware I can use to transmit information? Or how is a tumor working? Or what is the immune system doing? So therefore, we always group up with people from medicine, biology, chemistry, and work in close collaboration to tackle these challenges. So again, just because this is maybe something important, a takeaway, and also if you're interested in the field, just to get an idea about these challenges. Again, what does it mean to design hardware? So if we have such a scenario here, where we have maybe nano devices which can release drug molecules to treat a tumor, or we have nano devices here which are able to detect biomarkers, and they are then connected to the conventional communication systems like mobile phones or a smartwatch or something else by suitable interfaces. And hardware design now deals with the design of biocompatible devices for transmitting, receiving, and processing information. Interfaces and gateways, they are finally the connection between the Internet of Bio-Nanothings and the Internet of Things, and they transform these signals into each other. So they translate between molecules and waves, one could say. And we need suitable communication concepts and performance metrics, and that's maybe more the work of Christian then. And now, the thing that I will talk about, we need test beds. So we can develop all this theoretically. I can think about hardware, I can think about interfaces, I can think about communication methods and concepts, but without testing this somewhere, we will never go the way to any application. And therefore, these testbeds are indispensable for practical realization. And in the best case, these testbeds should be so close to reality as possible so that they can mimic these complex application environments. And now I want to talk about the first in vivo molecular communication testbed, which we are currently building up. So when we look into experimental research in molecular communication, and I start a bit earlier for all the ones of you who are not in the field, so this was the first Molcom testbed. It was a simple spray bottle with alcohol inside, and they sprayed. Basically, they encoded messages in the concentration of alcohol molecules. And on the other side, there was an alcohol sensor where they detected this information. So it's very simple, and it was horrible. That's why they placed the fan here, because the bit rate was not very high. And by the fan, they could increase the bit rate. But it is very simple, but it was really the first time that people encoded, let's say communication engineers encoded information into molecules. And this was also rather prominent. So in Canada, this was also on TV shows and in the newspapers and so on. This was 2013, and over the years, the testbeds became more and more complex. So here you can, for example, see one which is more based on tubes and different pumps, and they injected different acids and bases to encode information into the concentration of acids and bases. And then here you can see one testbed which was built at FAU some years ago. It's based on magnetic nanoparticles. So you can see here a background flow pump, which is mimicking basically the bloodstream. And then they injected magnetic nanoparticles, and they used the property that they are magnetic to detect them. And then one further testbed is also one from FAU, which is, this is the final version, which was finished recently, 2024. It's a closed loop testbed, so this means we are pumping all the time in a circle, and there are some photo switchable molecules inside. And by different types of LEDs, you can encode information into the state of these molecules. So the nice thing with that is that you can run these testbed over days without injecting anything or changing anything. You can repeatedly encode information into these proteins. So what we can see here, these testbeds became more and more complex, and they started to mimic more and more properties which are useful, for example, for medical applications. So for example, here we have tubes. So yes, this might be a rough approximation of blood vessels. Then here we use magnetic nanoparticles, and magnetic nanoparticles are also used in clinical practice. So they are, let's say, close to using in clinical practice. So they are practical carriers for drug molecules. And here, yes, it's also a tube, and it's also in a circle. And this is also one property of the cardiovascular system. So it's not that I inject something and then it's just going out somewhere. It's always going in a circle. So we had this significant process, but with a view on all these applications, the influence of living environments and the properties we have there, like organs and real blood and all these things, has not been studied comprehensively. And therefore, we wanted to go one step further by developing in vivo testbeds. And therefore, what we are investigating is the so-called Chorioallantoic membrane model. And you can forget the name. Let's just call it CAM model, because that's how it's used as an in vivo testbed. So let me explain what this is. So this CAM is basically formed in fertilized chicken eggs. So here on the right-hand side, you can see one of these fertilized chicken eggs. And I also didn't know how that is working. So when the chicken egg is developing, it starts to establish a vascular network into the white of the egg, which is just used as a respiratory organ. It's used to nourish the embryo. So because from somewhere it needs the oxygen and all the other nutrients to grow. So basically the CAM itself is just a membrane, and it's a highly vascularized extra embryonic membrane. And now what's happening, when I open the eggshell, I have an accessible model of a cardiovascular system, including blood circulation and organs. And maybe one important thing to say, this also fulfills the so-called 3R principles for the reduction, refinement, and replacement of animal models, because up to day 16, this does not count as an animal experiment. It's still very hard to do because you have to, let's say, take very good care of these eggs that they are not dying until day 16, but they don't have a nervous system, so they don't feel anything until day 16. And that's why this is one of the very great opportunities instead of using animal models. So looking at this on a first sight, this is perfectly suited for the development of new medical technologies and also for molecular communication in-body communication concepts. And we are doing that together with researchers from molecular medicine and microsurgery from the University of Regensburg and the Technical University of Deckendorf. Maybe let's shortly talk again about the components. So when we look at the topology, there are three main parts. We have the chick embryo itself, then we have the yolk bag, and we have the cam, so we have this vascular system which is outside the embryo. Again, this extraembryonic membrane is mostly formed within the 3rd and 10th day of embryonic development, and it's a highly vascularized network of vessels and capillaries. And then this cam is connected to the chick embryo, and this means it's also connected to the organs of the chick embryo at some day. Because in the first days, the yolk bag takes over the functions of organs. So for example, in the beginning, the embryo does not have a liver, so the yolk bag will very likely filter out everything which should not be there. And later, there are also organs like the brain or the liver. Then maybe interesting for us because we want to understand this as a communication system, or let's say as a small scale system which represents a cardiovascular system. Therefore, we need to understand the effects a little bit. So what's happening there? When I inject something, I have diffusion, I have flow, I have to account for this vascularization. I have a lot of different chemical reactions. I have sorption, so it means absorption, desorption, and also accumulation. So maybe before I explain the rest, let's look at one video. So here are two videos from our lab where we inject a fluorescent molecule and measure this over time. So this video is the first one to start. And then you can see, so this is a rather old egg, so that's why it has a very thick vessel on the top. And then when it's going down, it's basically distributing everywhere. So the areas which are not covered here, this is basically, you can see here the embryo itself. So for the flow profiles, so it has been shown that in most of the vessels we have laminar flow with, yes, the flow velocity has a huge range between micrometers and millimeters per second. And the diameters are also have a very broad range. However, also depending on the age, the organs and the yolk bag can have a strong influence on the propagation. Because similar to our body, when we inject something which our body does not like, the liver tries to take it out. And the same happens here. So after a while, these molecules will start to accumulate either in the liver, if the embryo is old enough, or in the yolk bag. And for us, experimentally, what makes it even worse is this: everything is changing because this thing is growing from day to day. And it's moving. So, but that is more a practical challenge, to be honest. Okay, here we can see another video. No, okay. Then maybe one big application. So the CAM model itself is very prominent in many research fields. So not in engineering, but in pharmacy and in biology, because it has many things which makes it a very, very good platform to test things. And one I want to, let's say, highlight is its increasing importance in tumor research. So for example, in tumor biology, metastasis, drug distribution, or molecular screening. Because what you can do, you can take either cancer cells, or you can, that's what the group in Regensburg is doing, you can really take human tumor tissue. So they do it when they have a patient, they take tumor tissue from the patient, and then they place it on the CAM model. And this tumor is then really connecting to the vascular system of the egg. So it's really vascularizing. It's even building metastasis after some days. you can show that because here we placed a tumor on the top of the cam. It vascularized, and then after 15 minutes, you can see that a lot of molecules accumulated here in the tumor. So this was just to prove the vascularization of this tumor. So what can they do now? They can take the human tumor tissue, place it on 50x, for example, and then they take different mixtures of drugs. What is the best for this type of cancer for exactly this patient? And that's one of the big benefits of this model. So even if this, let's say, engrafting of tumor tissue is rather challenging, if it's working, it's a cheap and very reproducible test platform for different types of drugs, for example. Okay, so now this was maybe a little bit more about biology. Now let's talk how this is related to a communication system by first redrawing that. So that was the first thing we did. We can rearrange this whole picture from before also as a communication system, or in our case, a molecular communication system. So we still have here the vascular system. We have maybe a tumor here. We have a syringe, we have the yolk bag, and we have the embryo. And then we can say, okay, we can have transmitters in there. And a transmitter can either be a syringe, so just an injection, or maybe if I want to study the released circulating tumor cells or something else, then also a tumor can be a transmitter. And I have many so-called natural receivers in the systems. So this means I haven't them placed arbitrary. They are just there. So for example, particles accumulate in the yolk bag or in the organs, and this can be counted as receivers. Then I can also place synthetic receivers if I want to do measurements. And finally, I have the channel. As the channel, I have this very complex closed loop vascular system. Then maybe to concretize this a bit more, depending on the application, we can specialize this general topology a little bit. So for example, if I want to study the molecule distribution and accumulation, and that is what we mainly did in the last year, then my injection would be a transmitter, the vascular system would be the channel, and then I have multiple receivers like the yolk bag or the organs where particles will accumulate over a longer time. Or what we also do, we want to study the molecule accumulation in tumor tissue, and that's basically the interesting difference here. Then still my injection is the transmitter, and my tumor is the receiver because there I want the molecules to go. But then also the organs and the yolk bag are part of the channel, because in this case, I don't want particles to accumulate there, but they will interfere the propagation because the liver starts to accumulate molecules, but they should go to the tumor. And finally, if I want to do some detection, I can also place some, let's say, synthetic sensors in this system. Okay, now our first goal was to understand this propagation of particles because the system itself is very complex and also very random. And what we did basically experimental and theoretical work side by side here. So for the experimental work, we injected fluorescent molecules into the CAM model and measured this fluorescence over a time and post-processed this a little bit with the goal to create a huge data set of this transient distribution behavior. And at the same time, we did theoretical work and tried to develop no exact models because that's really infeasible and we don't basically know the topology because we cannot see it. Therefore, we wanted to develop simple but insightful models to describe this distribution. And then we try to find some parameters which are hopefully also insightful about the system. Finally, we want to have some insights into the behavior of particles in these living systems, and also which effects play a role when we want to design a communication systems in such an environment. Before I show you some results on that, maybe one sentence about this modeling. Because one of the most critical things is here, mainly people consider at the moment just straight channels. I mean by that people just consider that, okay, my transmitter is here and my receiver is there. In between, I have a blood vessel, I have blood flow, I have chemical reactions, but they don't care what is behind, or they don't care what is before. But here we have to do that. So if I would consider here just a straight channel between, so let's say, some transmitter and receiver nanomachines, and I would release some molecules, then it would somehow look like that. So the molecules propagate by diffusion and flow, and when I measure here, I see one peak and then it's going down again. So that's a very conventional picture. But when I think about these realistic environments, which are highly dispersive and vascularized and especially closed loop, when I do here a measurement and measure the concentration here, what I can still see a peak, then it's going down, but then it's going to a constant value. And this makes also sense because the system is closed itself. So for the system theory people, the egg would have a pole at 0, while the upper part would not have one. And therefore, this requires also models which take these characteristic effects into account. But we are still engineers, so therefore modeling this exact topology is really infeasible. Therefore, we thought a little bit about the effects. Okay, what can we do with this closed loop effect? And we said, okay, instead of considering a straight line, we just consider a circle. So because this is already closed loop. And then what are the other effects? Yes, it's highly vascularized. So we expect that we have a lot of diffusion there. So we just used a very simple advection diffusion equation with an effective diffusion coefficient, which captures all this vascularization and dispersion, hopefully. And finally, the task was rather easy. We just had to solve this equation on a ring, and the solution is well known. It's a so-called wrapped normal distribution. So it's just a normal distribution, and then you map this to the domain of 0 to 2 pi. So here we can see this classical normal distribution, and this sum here just accounts for the multiple loops I can do in this ring. So now let's see how this model performs compared to measurements. So here on the left-hand side, what we wanted to do, we wanted to approximate the particle distribution in a region of interest, so measured somewhere in the egg. And that's how we did it. So this IXR, that is our measurement, and here's our approximation I hat. And this is obtained by the convolution of some injection dynamics. Yes, we have also estimated the injection dynamics. And then here we just convolve that with the model we have obtained on the slide before. And what I have not talked about is this sum here. Yes, we said, okay, it's highly vascularized, so maybe we allow the system to use multiple of these rings. Because when I inject, there might be one main propagation path, but there might be also a second path which is playing a role. Therefore, we just allowed the model during estimation, okay, you can take another ring if it's required. And then we estimate a set of parameters like effective diffusion, velocity, and distance, and the length of the ring. On the right-hand side, you can see the results. So this is taken from the data set, which the data set consists at the moment, I think, of 70 measurements, and it's currently all the time increasing. And what you can see here on the curves with the blue crosses are the measurement results. And the green curves are the approximations by just assuming that we have just one ring. And the red one allows already 2 rings. And what we can see, the approximate model with 2 rings is in really very good agreement with the measurement results. And I've not only chosen the best ones, so this holds over the data set. Therefore, our main conclusion is that, okay, this simple model is capable of approximating the particle distribution in very complex closed-loop vascular networks. So let's take a look into the parameters. So these parameters are not directly related to the physical parameters. That we cannot expect this because it's a too huge abstraction. However, let's see what they can do. So here on the right-hand side, you see the estimated diffusion coefficient. Oh, this seems a bit broken. So this is the diffusion coefficient over the day of embryonic development. This means these are just, let's say, the age of this egg itself. So the takeaway is that, let's just look at the colored points here, that most of these points group in, let's say, 10 to the power of -5 to 10 to the power of -7, which is very, very consistent over the data set. And now someone could say, okay, hey, this diffusion coefficient is very large. Yes, it is, because we are encoding in this diffusion coefficient all the effects we don't know, like the vascularization, the high diffusion, also the very, very small capillaries which are inside the CAM model. The flow velocity is down here. Also, this is the estimated flow velocity over the day of embryonic development. And similarly, we can see here that the estimation results are rather consistent here. And in this case, they are also not so far away from what is reported for the CAM model itself, because I said it's ranging from micrometers to millimeters, and we are also still falling in this range somehow. So what can we say? The parameters are consistent, and partly they are also in a very reasonable range. One thing before I come to an end, we also studied then after the distribution, we started to study the accumulation. Because as I said, the particles distribute very fast in the vascular system, and then they start to accumulate in the organs of the embryo. So we can see this here. So this is 0.5 seconds after injection. Then here it's almost distributed everywhere. And then after almost an hour, you can see that everything is grouped here. And now you have to trust me. So this here is the liver of the embryo in this case. And as the distribution is much faster than the accumulation, we can model this separately for a moment. And yes, this is just a picture from before. Now we not only consider injection and distribution, but also the accumulation in organs in this case. And I just brought two very simple results because at the moment we are working on a physically inspired model, but we started, okay, let's see if a very, very simple model can also fit this accumulation process. And we just used here this 1 minus exponential function, which is a little bit like a capacitor loading curve. And we can see this here. On the right-hand side, again, in blue, we have the measurements, and in red, we have this approximation. And we can see also here that is in very good agreement. And also the model parameters, which are not related to physics at the moment, are also somehow in a comparable range, what is also a very good sign that we are here also on a rather good way with that. Okay, I said all this. So now let's sum this up, because I'm almost at the end of my talk. The CAM model is a very versatile in vivo test platform. And for us, it's like, let's say, an important step for the transition of concepts to applications. It's a realistic environment, and it can be used in the best case for validation and optimization of these concepts. And we also showed that sometimes a simple analytical model is sometimes better than a very complex numerical model, for example, because we can also learn with simple models what's happening in such complex systems. And for us, this is, let's say, a first step towards a lot of exciting future research. And that's what I want to show you in the end, which are 3 projects, which all start this year on this CAM model, basically. The first one is one project which will start later this year on drug delivery, where we expand exactly what I showed you before, that you can engraft tumor tissue and test drugs. So how can we combine this with our, let's say, more communication theoretic thinking? What we want to do is like we take different types of tumor materials to create a database how different types of tumors take up molecules over time. And then with that, you can finally develop models for the distribution and this uptake. And hopefully you can develop then a concept for treatment and on, let's say, real-time optimization of the treatment to increase the amount of drug molecules which are reaching the tumor. The second project is more a practical project with researchers from microsurgery, which already started last year. So here on the left-hand side, you can see that basically microsurgeons are very smart people, so they can just, let's say, put small pieces of tubes into a vessel. And one of the big challenges in molecular communication is how can we place biosensors inside the bloodstream. And on the other hand, there is something which is called a venous coupler. It's a little bit like Lego. So you can cut the vessel and then you place the couplers on both sides and then you can plug this together again. And now, together with people from microsurgery, we are bringing this together by basically taking this tube and putting the couplers on both sides so that you can basically plug and play implanting of a piece of tube. And in a second stage of the project, this piece of tube is pre-functionalized with a biosensor. And then especially when we talk about during operation monitoring, such devices can be plugged in to live monitor some biomarkers during a surgery or something. And the last project is a project which starts tomorrow, funded by the European Union, together with people from Italy, Finland, France, and also Germany, where we also use the CAM model, but also other in vivo models and in vitro systems, where we want to develop communication concepts. And now this is a bit more classical between implanted devices, because also implanted devices can be extended by, let's say, the possibility to receive or release molecules, and then you can develop more network on a networking level communication concepts between these devices. And also a partner from Finland will take a look into the secure communication between these devices and external devices. Okay, so now this is also an advertisement. We are still hiring, so if you're interested in doing, so not a PhD, because I think all of you are doing a PhD, but we have open positions for PhDs and postdocs to work with us on these projects. And finally, I want to thank all the research group at FAU. So this is just a part. We grew a lot more now. All our collaboration partners and funding bodies. And finally, also thank you, Christian, for the invitation. And this ends my talk, and I'm happy to answer any questions.
If I assume that these little chicks grow older inside of the egg, I would assume that the complete vascular system changes completely. But if I look at your diagrams, I can see that depending on DED, there is practically no change, although the vascular system has to change because the chick grows.
Yeah, that's right. So this is so one parameter I've not shown is this effective length, for example. So the length of the ring. So this one is really changing with the age a lot. And the second thing, what we can see with the age is that when you look, for example, at the estimated diffusion coefficients, that the variance is becomes smaller and smaller with the age. And that is something what we also say, okay, this must have to do with the growing, because as older it is, it's very likely that you have one main transport vessel, which is, let's say, very dominant on the top or something. Yeah.
And I have a second question, if I may.
Yeah, sure.
What is the effect of the egg prices in the United States through your?
So luckily it's not affected, because we are doing this in Regensburg, and they have a very nice agreement with a local farmer. Because I have to say, so it's rather really challenging to keep these eggs alive, because you're opening the shell, and so they are it's very likely that they get infected. You can also just take them out for some hours from the incubator. So you need also good eggs. So, and with this farmer, it's working very well. So it's worse if you're in winter, because then there are less eggs, unfortunately.
A follow-up question regarding the first one. So
Okay.
There is a heart beating, right?
Yes.
But you can neglect that impact because it's beating very fast, or what's the reason why you don't model that?
Yeah, we wanted to include that too in a later step, but the thing is that the model we envisioned here is super abstracted, and that's why we thought, okay, let's neglect this also for a moment, because finally the heart is really beating very, very fast. And we think it must not have such a big influence, but we are doing also studies where we partly try to model this in more detail to really study which effects it really has. Yeah.
Perhaps you can say at the last slide, you say something about security. So what do you mean with this, and how you want to communicate securely?
So I'm the wrong person to ask. As I said, so this is like in a larger consortium, and there's a group from Finland. So they are from ambient computing and secure communication based on ambient computing. But how they want to do it, I can answer you in 2 weeks, because the project kickoff is on April 6th. So at the moment, I don't know which ideas they have to do that.
Perhaps another question. So mainly in the first part of the talk, or in the middle part, you talk about how to communicate to fight against diseases somehow. But at the end, also one goal of this bio nano things is also to do doing some health care, to keeping care of health, and also to communicate in this way. Can you also have you some idea how you can test this with your eggs, or to monitoring?
You mean health monitoring?
Yes.
Yeah. So it's like one part of, or one idea of the project is, or of these projects is also that at some point we can take these biosensors and put them into the eggs. Because you can really measure things in there, because you can engraft tumors, so you can also measure biomarkers which are released by tumors. But this is like, it's not easy because the concentrations are very low. But I would say yes, and you can also do a lot of other things with these chicken eggs in terms of monitoring. So you can do ultrasound and all these other things. So yes, it's also a nice test platform for biomarker studies, for example. Yeah.
Okay, yeah, thank you. So, some more comments?
I have one question. How are you measuring the basically you have these molecule concentration curves kind of? How are you measuring that at the moment, just from the camera and the pixel color of the
it's like
fluorescence?
so we have this camera in different overlays. So it's a very high efficient ICG camera. So it's the fluorescent molecule we are using is something which is more used in clinical practice for visualization of vascularization during operations, for example. So this is a high performance camera with a laser, especially tuned on this wavelength for this particular molecule. And then there is, exactly for that, there's an analysis toolbox for exactly this ICG videos. And from that, we basically extract the curves, assuming that it's knowing that it's more or less proportional between the intensity we are measuring and the concentration of molecules. Yeah.
Okay, thank you. So there's basically, this is like highly developed to kind of account for maybe obscuring across layers, right? Because you're only looking at it from one side, and there might be something going on below, but this is optimized, right?
But so one thing we have to take care of, so these cameras are basically optimized to, let's say, bring you always the best picture. So they scale a lot. So that is something we have to get rid of. But there's like in the videos, we place a lot of reference points, for example, to get rid of the scaling. But one thing we have to take into account in the future, and this can be also seen, and this is also a reason why these diffusion coefficients we are estimating are so large, because if you look in the video, one thing is like you have these multiple layers, right? Because it has a depth. And you can see that there's always below your one vessel, there might be fluorescence from other vessels. And that's also the reason why the diffusion coefficient is so large, because if you are, maybe not in this view, but I have other ones where you can see it more, it looks a bit like, so how it looks is that you have really a diffusion front, which is distributing over this network. And that's why the diffusion coefficients are so high. And yes, in some way, we also have to, let's say, take into account how it's working when you look into the, let's say, deeper vessel network here. But at the moment, we are happy that we can, let's say, consistently just approximate this with the Model 2. What we also did, you can, if you are more talented than I am, you can take really a vessel from the egg and put it a bit out, and then you can place something below the vessel, so just like a black part of plastic, and then redo, for example, the measurement. And we did this too, but finally it was too much work, and you don't gain so much information. So yeah.
All right, thank you.
Okay, then thank you again.